Okay, here we are, term 2, first unit. Okay, the first two lessons are about curve fitting, okay, and then we go on to geometric series. So these are really for your assignment, okay, so you know what to do, know what R-squared values are, and things like that. Alright, so we'll have a look at curve fitting and what R-squared values are. So let's just imagine we collect some data. We've got two variables, variable y and variable x, okay. It could be anything, doesn't matter what they are. Trying to draw a line of best fit through this data to establish some relationship between them. I look at that data, I think, oh yeah, apart from this guy at the top, looks pretty linear. Okay, so I'm going to attempt to fit a linear line of best fit through the model. Okay, so whatever you've done in history or geography or those sorts of subjects, you'd try and draw a line of best fit. You'd get some line and draw it through so that roughly same amount of points are on either side of the model. Yeah, you might look at my model and say, well, maybe it should be further down here. Okay, it's because it'll mean more points are either side. It's sort of more average. Okay, everyone can have a go at drawing a line of best fit, and would probably get different values. Okay, once I've drawn the line of best fit, we could find, so I'll just assume it's that first one. We have here our C value, and then we just choose two convenient points, okay, to find our gradient, and we'll be able to draw the line of best fit. Okay, so issues with this are inconsistent. Okay, we may get different lines of best fit. Alright, so the way that we get around this is to make sure we actually get the line of best fit is use this thing called the method of ordinary least squares. So what your computer, what Excel or your calculator will do is it'll try every single line available, okay, and it's going to minimize these distances from the data points and the line. Okay, so it does it relatively quickly, okay, but puts all these points into some algorithm and it'll generate the line of best fit. Okay, and there's only ever one line of best fit using this OLS, the ordinary least squares method. Okay, you don't really need to know about that, but what you do need to have an idea of, okay, are the two things that it spits out. Okay, so the model, it produces the line of best fit. Okay, so the y equals mx plus c. Okay, and it also produces this r squared value, okay, which is called the coefficient of determination. Okay, which is going to tell us how well the model explains the data. Okay, I guess the formal definition of r squared is the explained variation divided by the total variation. So we can look at the best case and worst case scenarios. Okay, the worst case scenario, we've got these data points, okay, lots of variation between them. Okay, in this case, our model just finds the average of them and doesn't try to explain any of this variation. So there's all this variation out there, okay, away from away from the mean value, so it might be the average weight of the class. We've got people heavier, we've got people lighter. It varies heaps. This model doesn't explain any of that variation at all. It just says, yeah, just find the average, put a line through it. Okay. This R-squared value would be 0, because it doesn't explain any of the variations. Okay, alternatively, an R-squared value of 1 would be where our model, our straight line, explains every single piece of data 100%. Okay, so our model gives reasons for some people being heavier, some people being lighter, okay, and the reason would be whatever this variable is. Okay, it could be what you eat at home, could be how much exercise you do. Okay, most likely what you eat at home, because this is increasing. Okay, so it might say how many chocolates you eat per day, 1, 2, 3, 4, 5. This will exactly determine your weight. Okay, it's unrealistic usually for us to get R-squared values of exactly 1. Okay, we'll normally get something between 0 and 1. Okay, given that we'll most likely be able to explain some of the variation in our data. And we'll look at that in a few examples. Okay, I guess just to solidify this idea of the R-squared, most of our models are going to look something like this one. Okay, in that we've got a whole heap of these data points. Our line of best fit goes through them. It doesn't exactly fit all of the data points. Okay, there's a bit of variation. It could be experimental variation. Could be that our variable here doesn't explain all of the variation in the data, and we'll look at that in a few examples. Okay, what it really does is from that useless model, okay, from that average model, we see that there is some variation. Okay, this total variation. Okay, and with our model, with our red line, we've been able to explain that much of the variation. Okay, so I'd find whatever this distance is, explain variation, find this total variation, okay, and divide the two, and express it as a decimal. You see in this example, from our useless model, we've got this variation, okay, total variation. The amount of variation that we've explained is the same. Okay, so if I was to do explain divided by total, whatever this distance is, say it's 5, I'd get 1, okay, because I've explained all of my variation. Okay, hopefully that gives you some idea of what these R-squared values are. So let's have a look at doing a few models. So when we put the line of best fit, okay, it's also called doing a regression. Okay, aka regression. All right, let's investigate some variables, see if we can find relationships between them. So I grabbed a whole heap of data from the Census at School website. Okay, this is actual real data from around Queensland, and it's got the students' year level and their height. Okay, so you see in the height, there's lots of variation. 62 centimeters. All right, I'll leave it in there. Okay, lots of variation in the height. Okay, what we want to see is that variation in the height, how well is it explained by the year level? So I'm going to highlight these two columns, insert a chart, I'll insert a scatter plot. And I look at this scatter plot and I see, well, as the student's year level, so I should put some chart titles on here. Access titles, primary horizontal. Okay, as the year level increases, it looks like they're gradually getting taller, okay, which is sort of what we expect. I think it's a linear relationship. I think each year you get older, you're going to increase in height in the same amount. Okay, that's my theory. So I'm going to test my theory. I'm going to click on these data points. I'll right click it and add a trend line. Okay, I'm going to attempt to add a linear trend line. So that dotted line is my trend line. Okay, that's my line of best fit using ordinary least squares. Okay, I think it's linear. I want to know what's the equation of that line, and I also want to know what the R squared value is. So in my trend line options, I've got linear because it's a linear line. I want to display the equation, and I also want to display the R squared value. I'll move them to somewhere where I can see it. Okay, so my equation is y equals 4.22x plus 126. All right, so the 126 would be my y-axis intercept if I continue this line across. So when they're in preschool, they should be 126 centimeters tall. Yeah, it's probably about right. And this 4.22x means each year you increase, your height should increase 4.22. Okay, that's the idea of the linear model. Let's just focus on the R-squared value here. So the R-squared value is 0.3293. Okay, so what I can write is the model explains 32.39% of the variation in height. Okay, that is a person's year level is responsible for 32.39% of their height. Okay, so the year level determines their height, but only 32.39%. Okay, what other reasons do we have for people's height being different? You can probably think of a whole heap of other reasons why. Okay, some could be their parents' background. Okay, could be diet. Could be their age. Okay, whether they're born in Jan or Feb. Okay, it could be hormones. Okay, it could be gender, male or female. Okay, we don't have any information about any of those things. All we're just looking at is how the year level explains their height. Okay, and it doesn't do it particularly well. Okay, it only explains 32.39% of the data. 32.39% of the variation in the data. So this linear model that we've tried to fit may not be the best model to fit. Okay, and our theory that as a person's year level increases, their height increases, it's true, but there's other reasons for people having this varied height. So I'll try and get a bit more specific, okay, and do a bit more analysis. Okay, the people actually put their birthday in here as well, so I've just mashed it into Excel to see if I can graph their age versus height. So I'll do the same thing, insert my scatter plot. Okay, there's someone who's 0 years old and there's someone who's 60 centimeters tall, but it's okay. I'll click on my data, add another trend line, okay, add a linear trend line again. And I need to make sure I display the equation and the R-squared value. All right, so again, a linear model with a person's age and the height. Okay, only 0.2682 of the data is explained. Okay, one of the things with these regressions are these outliers will have a big effect. Okay, so this line is pushed up a little bit because of that that outlier and this one. So I'm just going to try and find this data, because I don't think there's anyone that's 0 years old, and see if I can remove it. Okay, so that's just the problem with my data pre-1992. Sure. Okay, so I've got plenty of data. Don't need you. Got a 9-year-old in school. That's okay. And this guy that's 60 centimeters. So see the R-squared value is already increased here to 37.11. I'll get rid of the 60 centimeter person as well. And that's probably just an outlier data. Maybe someone either just having a laugh, or it might be legitimately really short. Okay, but since I removed them, I can see the person's age is a better determiner of their height. Okay, so again, we can write the linear height versus age model explains 46.87% of the variation in height. Okay, which I think is pretty good, 46%. So again, we've got those other reasons. Okay, so other reasons for variation in height. I can copy most of these across. Okay, parents' background, diet, get rid of age. Okay, and gender could be in there as well. We don't know anything about the gender of the people in here. They could be males and females altogether. A good thing would be to just strip out all of the males and all of the females and produce 2 of these graphs separately, okay, to try and control those other variables, okay, those other things that may be the reason for the variation in height. Okay, so this is a better model, more explanatory power, okay, and more useful for making predictions. Okay, remember, once you get these models, you can do predictions. Like I could say, how tall would someone be who is 25 years old? Okay, 25, put in x equals 25 and get the height. And also do the same thing with the height. So how old would someone have to be 5 meters tall? Well, they'd have to be 100 years old. Okay, you might think that's ridiculous. Okay, so we'd probably have to make some comments here. Okay, the model is only valid for x values between, let's say, 8 and 20. Okay, model. Okay, so it's really important to think about your domain in all of these curve fitting problems. And just think about the R-squared value being an indication of how well this linear model explains the variation in the data. Okay, it's probably the key language we want you to use. Okay, 2 more quick ones that I'll sort of power through. So hours homework versus age. So I've got the person's age and the amount of hours homework that they do. Again, insert scatter plot. It's all over the place. So the question is, as you get 1 year older, I think like in the diary, it says the amount of hours study you should do is basically your year level. So if you're in year 11, do 11 hours, year 12, do 12 hours. So it should be a linear relationship. I'll see how well that idea fits. Okay, linear, display the equation, display the R-squared. Okay, it's only 5%. Okay, so a person's age only explains 5% of the variation in hours homework completed. Yeah, it's not a very good model. Okay, the model doesn't explain much at all. Okay, other variables affecting homework. Okay, could be parental influence, could be motivation, could be amount the teacher nags, all of those sorts of things. Again, we've got some outliers here. I might just try and get rid of these 40 people. Okay, I don't think. I hope there's people doing 40 hours study, but just to see how the model changes. And actually explained it less, getting rid of them. Okay, so there was only 3% with them gone. Okay, so those are that's a pretty bad model. A model that should be better should be year level versus age. Okay, so as you get older, does your year level increase? Okay, hopefully it does. So let's set this. Look at this. I see, yep, that looks like a pretty linear relationship. Okay, each year you get older, you should be going into another grade. I'll right click these, add my linear trend line, display both of these. Okay, so as my age increases, yeah, I'm going into a higher year level. Okay, remember this is age on the bottom side. There's some outliers here. What do we got? Someone that's, if I could remove these outliers, I'm just not sure where I'll find those exactly. So yeah, 8. Ten-year-old in year 8? I don't think so. Thanks for trying. 17-year-old in year 9? Okay. I've had that before. 12-year-old in year 10? Don't think so. 21-year-old in year 12? Yep, seen that as well. So all those things are okay. Okay, and we get an R-squared value of about 90%. I think some people have a rule of thumb that 90% is a good way of testing whether a model's okay. You'll get some models above 90%. Have really good explanatory power. Okay, so I'd write here a person's age explains 89.76% of the variation in year levels. Okay, other reasons could be kept back a grade. It could be more babies in certain months. Okay, it could be international students older than their peers. Okay, all those sorts of reasons are there. So at the moment, all we've really looked at are linear models, okay, and their explanatory power. The final model we'll look at is a quadratic model. Okay, so what I've got is some data from dropping a ball. So at time 0, the ball is 1.55 meters high. Okay, as the time increases, the ball drops to the ground. If you've done year 10 physics, you should know that this should form a parabola, okay, an x-squared curve. So if I went ahead and tried to, so that's time on the x-axis, this is height here. If I try and add a trend line here, my linear model, if I can put the equation r squared, Yeah, it does a reasonable job. 95% of the variation is explained by a linear model. Okay, but we can see in this data it's a quadratic model. So what I should really be doing is getting rid of my linear model, and when I add trend line, okay, a polynomial, which is like a quadratic or a cubic of order 2, okay, means quadratic. Okay, that dotted line of best fit looks pretty good. Equation r squared. Let's have a look. So there's my equation. It's quadratic. So an x squared and x terms looks good. And 1.533 is my y-axis intercept, which is pretty much where it started from. My r squared value of 0.99. Okay, it says that the time in flight explains 99% of the variation in height. Okay, so when we say the time in flight, we're really referring to the laws of physics. Okay, or the kinematics and those sorts of things. Other reasons, so how do we explain that 0.01%? Things like wind resistance. What else? So one of the big reasons is experimental error. Okay, so data collection, and the wind as well. Yeah. Alright, so that's the way we can fit these different trend lines. Okay, we've also got options for exponential trend lines. Can't seem to click exponential here. Maybe if I get rid of this last data point, it'll allow me to. Yeah, so if you've got a 0 in your data, you won't be able to access exponential. Okay, I wonder what the r squared value is here, 0.74. Yeah, understandably low, okay, because we know it's not exponential. Yeah, all these different options of trend lines to choose. Last thing I just need to quickly show you is how to use a graphics calculator to do this. So I'll choose one. I'll choose this age versus height. So I'll only fill in this amount of data because you don't get many YouTube likes by just entering data all day. Okay, so I'll enter my data into stat menu. So I'll just type a few of these lines of data in. Should have prepared this earlier. Okay, so I've entered my data in list 1, list 2. I'll draw a graph of what it looks like. Okay, just go into set menu, make sure we've got a scatter plot with list 1 and list 2. Okay, so I want to graph it, see what it looks like. Okay, there's my linear relationship. Okay, to draw a line of best fit, I'll press calc. And here are all my options. So x is a linear model, x squared for quadratic, x cubed for cubic, quartic models, logarithmic, exponential, power, sine. So calculator can do everything that Excel can. I was trying to fit it to a linear model. Okay, here we go. A little bit more effort than on Excel. So it's telling me y equals ax plus b. A is 6.15, so y equals 6.15 x plus b, which is 61.89, and there's my r squared value of 95.92. Okay, if I could somehow paste all of this data in here, I would get exactly the same line of best fit and r squared value. Okay, so it's a brief rundown of what r squared values are all about. What you are going to do in class is have a go at this curve fitting problem where you look at this data, okay, and see how the person's height is better explained. Is it better explained by the wingspan, or is it better explained by the foot length? So you're going to have to produce two graphs, see which one has more explanatory power, and make some conclusions from there.